Right now, a machine sits frozen on the moon, waiting 2 weeks in darkness so cold it could shatter steel. Above it, radiation pours down with nothing to stop it. Below it, the ground quietly cracks and shakes. We keep promising a permanent moon base. We keep failing. Today we travel to a world of razor dust, month-long nights, and craters colder than Pluto to uncover the real reason humans may never truly live there. If wonders like this pull you in, like and subscribe. Now hold on tight. We begin. 6 American flags stand on the moon right now. The sun has bleached every one of them pure white. 12 men walked up there between 1969 and 1972. Then something strange happened. We stopped. Look at that gap. 50 years. Longer than most people watching this have been alive. We built machines that carried humans 250,000 miles across empty space, landed them softly on another world, and brought them home. Then we packed it all away and turned back to Earth. People assume we quit because we ran out of things to do. The opposite is true. We had barely scratched the surface. The last crew, Apollo 17, spent 3 days driving across a valley and found rocks that rewrote how we understood the moon's birth. They left with the science just beginning. So why did we leave and stay away? The answer starts with money. Each Apollo mission cost a fortune. At its peak, the program swallowed close to 5 cents of every tax dollar the American government spent. That kind of spending had one real purpose: beat the Soviet Union to the moon. Once the race was won, the reason to keep paying vanished. Here is the part that stings. Getting to the moon for a few days is one problem. Staying there is a completely different one. A visit is a sprint. You pack your air, your water, your food, you plant your flag, you leave before anything breaks. You never have to survive the place. Living there means facing every horror the moon can throw at you, over and over, forever. And the moon has a lot of horrors. Picture a beach, warm sand, soft waves, a gentle breeze. Now strip away the air, strip away the water, strip away the sound, freeze it to hundreds of degrees below zero for 2 weeks, then bake it hotter than boiling for 2 weeks more. Fill the sand with tiny glass blades that cut and cling and never stop. That beach is the friendliest spot on the moon. Every space agency on Earth now says the same bold thing. This time we will stay. This time we build a base and never leave. The United States says it. China says it. Companies with billionaire owners say it. Beautiful drawings show glowing domes and happy astronauts farming under the stars. Yet the deadline keeps sliding. The first permanent moon base was promised for the 1980s, then the 2000s, then 2020. Every promise has slipped. Every plan has stalled. There is a reason for that pattern. A deep one, buried under all the shiny pictures. The moon fights back in ways that break machines, sicken bodies, and drain fortunes faster than any nation can refill them. Over the next chapters, we will walk across that broken world one danger at a time. We will feel the dust that ruined the first astronauts. We will stand in a night that lasts 2 weeks. We will crawl into caves no human has ever entered. And by the end, you will understand something most people never hear. The reason we may never truly live on the moon has almost nothing to do with rockets. It starts with something far smaller, something you cannot even see until it is already inside you. Stand on the moon at noon and look up. You see black, pure, total black, with a white sun burning in the middle of it. No blue, no clouds, no haze. The sky of every daytime you've ever known is gone. That missing colour is your first warning. It means the moon has almost no air. On Earth, air does quiet miracles all day long. It scatters sunlight into a soft blue dome. It carries warmth from the sunny side of a rock to the shady side. It slows down anything that falls from space until it burns up. It presses gently on your skin and fills your lungs without you ever thinking about it. Strip that air away and everything changes at once. The first thing to break is shadow. On Earth, step under a tree on a hot day and the shade feels cooler, but only a little. The air shares its heat around. On the moon there is no air to share anything, so a patch of sunlit rock can sit at a temperature hotter than boiling water, while the shadow one step away sits hundreds of degrees below freezing. Picture standing with 1 foot in an oven and 1 foot in the coldest freezer ever built. That is a single step on the moon. This makes the moon a world of knife-edge lines. Light and dark meet with no blend between them. Astronauts describe shadows so black they look like holes cut into the ground. You cannot see into them at all. A rock, a dip, a crack. Anything hiding in that shadow stays invisible until you're right on top of it. Now think about driving a rover through that. Your headlights barely help because there is no air to spread the light. One side of every boulder glows. The other side is a wall of nothing. Explorers have already reported the strange dizzy feeling of losing all sense of depth. The ground plays tricks. A small crater and a deep pit can look exactly the same until you fall in. The thin air causes a second problem too. Sound dies. On the moon, you can stand beside a crashing landslide and hear silence. With no air, there are no sound waves. If a machine near your base tears itself apart, you will feel the ground shake before any warning reaches your ears, because a warning by sound cannot travel. And there is a third danger, quieter than the rest. With no air to slow them, tiny bits of space rock slam into the surface at full speed. On Earth we call them shooting stars, and the air burns them up miles overhead. On the moon they hit the ground like bullets, some no bigger than a grain of sand moving faster than any rifle round. A base sitting in the open would be peppered by them, day after day, year after year. So before we even talk about the famous dangers, the cold, the radiation, the money, we have to face this simple truth. The moon took away the one thing that makes Earth gentle. It took away the air. And every horror that follows grows out of that single missing gift. The worst of those horrors is already waiting under your boots. It looks like harmless grey powder. It is the most dangerous dust in the solar system. Scoop up a handful of moon dust and it looks like grey flour. Soft, harmless, almost cosy. That look is a lie. Under a microscope, each speck turns into a weapon. The grains are jagged, sharp, shaped like broken glass and tiny spikes. Some are so fine they behave like smoke, yet every one of them has edges that can score metal and slice cloth. Here is why they are so cruel. On Earth, dust gets old and gentle. Wind rolls each grain around. Water tumbles it down rivers. Over thousands of years, the sharp corners wear away, and sand on a beach becomes smooth enough to run through your fingers. The moon has no wind and no water. Nothing ever softens its dust. So these grains have stayed razor sharp for billions of years, frozen mid-scream since the day they were made. And how they were made is the strange part. The moon has no soil in the way Earth does. Its dust was born from violence. For billions of years, space rocks have crashed into the surface with nothing to stop them. Each impact shattered stone and melted it into tiny glass beads and splinters. The whole top layer of the moon is ground-up wreckage from a war that never ends. Scientists gave this layer a name, regolith, but the plain truth is simpler. The moon is covered everywhere, in a blanket of powdered glass. Now, imagine trying to live on it. Every step you take kicks up a cloud. That cloud hangs in place because there is no air to carry it and no breeze to blow it off. It rises, floats, and settles right back down on you. Walk for an hour, and you are coated. Kneel to pick up a rock and your knees grind into glass. The Apollo astronauts learned this the hard way, fast. After only a few days, their bright white suits had turned filthy grey from the knees down. The dust worked its way into zippers. It jammed the joints of their gloves. One commander found the seals on his suit so clogged that he could barely move his wrists by the end of the mission. And these were visits that lasted 3 days. A permanent base means people out on that surface for months, years. Every single day adding another layer of glass to every moving part they own. Think of it like sawdust in a workshop, except the sawdust is made of broken glass. It never sweeps away, and it clings to your body like it is trying to get inside. Engineers have a word for what dust does to machines: wear. A little dust wears down a seal slowly. A lot of dust wears it down fast. And on the moon there is always more dust, endless dust, working its way deeper with every hour that passes. A base is only as strong as its weakest seal. One worn gasket lets the air leak out. One jammed joint traps an astronaut in a broken suit. The moon can defeat us with a patient disaster, grinding away grain by grain, with no need for anything dramatic at all. But the sharpness is only half the nightmare. These grains have a second trick, a hidden power that makes them almost impossible to shake off. They are electric. The dust does something no dust on Earth would dare. It reaches out and grabs you. On the moon, sunlight is raw and unfiltered. When it strikes the surface, it knocks tiny charges loose and leaves the dust electrically charged. You have felt a weak version of this on Earth. Rub a balloon on your hair, and your hair stands up and clings to the rubber. That same force, static electricity, is alive across the entire moon. Charged dust behaves like it is haunted. It levitates. It creeps up walls. It leaps onto anything nearby and holds on with a grip that brushing cannot break. Astronauts tried to wipe it off and only smeared it deeper. They tried to beat it off their suits, and it sprang right back. There is a photograph that tells the whole story. When Apollo 12 landed, the astronauts walked over to an old robot probe called Surveyor 3, which had been sitting on the moon for years. They wanted to bring pieces of it home. When they studied those pieces back on Earth, one side was caked far thicker with dust than the rest. That side faced the spot where their own lander had touched down, more than a football field away. Their landing had flung charged dust across the length of a soccer field, and it had clung to the probe like iron filings to a magnet. Now carry that into daily life at a base. Every time an astronaut comes back inside, the dust comes with them. It rides in on their suit, glued tight by static. Airlocks are supposed to clean them off first, but blowing air at charged dust is like blowing at a magnet. The grains hold firm and slip through anyway. Inside the base, they float free in the low gravity, drifting into eyes, into food, into the fans and filters that keep everyone breathing. The Apollo crew smelled it the moment they took their helmets off inside the lander. They said it smelled like gunpowder, or like the sharp air after a fireworks show. Fine glass powder, floating in their cabin, going straight into their noses and lungs. Engineers have thrown everything at this problem. Special coatings that shed dust, brushes and wipers, even devices that try to zap the charge away with waves of their own electricity. Some show promise in a lab. On the real moon, at full scale, for years on end, none has ever been proven to work. Here is the deeper worry. A base has thousands of moving parts, doors that must seal, wheels that must turn, solar panels that must stay clean to catch the sun, radiators that must stay clear to shed heat. Charged dust attacks all of them at once, quietly, constantly, with no off switch. One clogged panel means less power. One coated radiator means the base cannot cool itself. One sealed door that will not seal means the air escapes into space. The dust attacks whichever system it reaches first, then moves to the next. It only keeps coming. So the moon hands us an enemy that is sharp, endless and electric, an enemy that hides in grey powder and never sleeps, and we have barely begun. Because that same dust, the stuff that ruined the suits and floated through the cabins, has already found its way into the one place no one can afford to lose. It has gotten inside human lungs. Harrison Schmitt was a trained geologist, the only scientist to walk on the moon. He had studied rocks his whole life. Yet nothing prepared him for what happened when he pulled off his helmet inside the lander. His eyes watered, his throat scratched, he started sneezing. He called it lunar hay fever. Within hours, his face felt raw and stuffed, like the worst allergy attack of his life. And he was one of many. Astronaut after astronaut reported the same thing: coughing, sore throats, a stinging in the nose that would not quit. They had breathed the dust, and their bodies were fighting it. Here is what makes lunar dust so dangerous to breathe. The grains are unbelievably small. Many are finer than the particles in cigarette smoke, particles that tiny slip past every defense your body has. Your nose cannot trap them, your throat cannot catch them. They ride the air all the way down into the deepest corners of your lungs, into the little sacs where your blood picks up oxygen. And there they stay, sharp, jagged, chemically hungry. There is a second twist that makes it worse. On the moon, the dust has spent billions of years being blasted by raw sunlight and space radiation. This leaves the grains chemically reactive, almost hungry to bond with whatever they touch. When they land in the wet tissue of a lung, they react, they irritate. Some scientists fear they could scar the tissue over time. We have seen a version of this horror on Earth. Coal miners who breathed rock dust for years developed black lung, a disease that slowly turns healthy lungs into stiff, scarred, failing tissue. Workers who breathed fine silica dust, which is a close cousin to some moon dust, got a disease called silicosis. It cripples the lungs. It has no cure. Now picture a moon base. People living there for months, maybe years. Every trip outside brings dust back in. It floats in the low gravity, refusing to settle, drifting through the air everyone breathes. The Apollo crews only faced it for 3 days and still got sick. What happens to a body that breathes trace amounts of powdered glass every single day for a year? Nobody knows. And that uncertainty is its own kind of danger. Doctors cannot run the experiment safely on Earth because we do not have real moon dust in large amounts, and what little we have is too precious to grind up. So we send humans to the moon partly blind, hoping the filters hold, hoping the damage stays small, hoping we can clean the air faster than the dust can fill it. Think of the lungs like a house with the windows open in a sandstorm. You can sweep all day. You can run every fan you own. But if the sand keeps blowing in, the house keeps filling. Sooner or later something clogs. A base can survive a broken machine. You can fix a machine. You cannot swap out a crew's lungs. The dust that threatens the equipment threatens the people even more, and it does its damage in silence, breath by breath, where no one can see it happening. We have spent 5 chapters on a single enemy that fits in the palm of your hand. Now the moon reveals a threat you cannot hold at all. It is about to turn out the lights for 2 entire weeks. We think of a day as something simple. The sun rises, crosses the sky, sets, and darkness comes. Wait a few hours and it rises again. On Earth, that whole cycle takes 24 hours. On the moon, 1 day and night lasts about 29 Earth days. Read that again. A day on the moon is nearly a month long. The sun creeps up slowly and hangs in the black sky for around 2 Earth weeks. Then it sinks, and darkness falls for another 2 Earth weeks. 14 days of light. 14 days of night. Over and over, forever. This happens because of how the moon turns. It spins very slowly and it always keeps the same face pointed at Earth. That slow spin stretches each day into weeks. A person standing at a moon base would watch the sun take days just to climb from the horizon to overhead. At first that might sound peaceful. 2 weeks of endless daylight to work and explore. But the night is where the trouble hides. 2 weeks of darkness is a very long time to survive on another world. On Earth, no matter how cold a night gets, the sun comes back in a few hours and warms everything up. Your body knows this. Your machines know this. Every heater, every battery, every living thing on Earth is built around the promise that morning always comes soon. The moon breaks that promise. When the sun goes down, it stays down for the length of a school vacation. And during that long dark, the temperature does something that would destroy almost anything humans have ever built. Here is a way to picture the strangeness. Imagine your hometown, but the sun only rises once a month. You would get 2 weeks of continuous daytime, where the sun never sets even while you sleep. Then 2 weeks where it never rises at all, and every clock, every meal, every bedtime happens in total darkness. That is normal life on the moon. This long cycle wrecks the simplest plans. Solar panels are the obvious way to power a base, because the sun in space is strong and steady. During the 2-week day they work beautifully. Then night falls, and for 2 weeks they produce nothing at all. A base running on sunlight would go completely dark right when it needs power the most to stay warm. It wrecks the human mind too. Our bodies run on a hidden clock, tuned over millions of years to a rising and setting sun. Astronauts already struggle with sleep in space. Now give them 2 weeks of unbroken daylight followed by 2 weeks of unbroken night. Their inner clocks would spin out of rhythm, throwing off sleep, mood and focus in a place where one tired mistake can kill. Some spots near the moon's poles get almost constant sunlight on high crater rims, and space agencies are racing to claim them for exactly this reason. But even those spots have long stretches of shadow and the ground below the rim can stay dark for weeks. There is no perfect hiding place from the rhythm of the moon, so the moon takes our most basic comfort, the simple return of morning, and stretches it into something alien. A base must be built to survive a night that stretches as long as a month, and that night gets far worse than dark, because when the sun disappears, the temperature begins to fall toward a number so low it barely feels real. The coldest natural place ever recorded on Earth is a spot in Antarctica. It reached about 140 degrees below 0 Fahrenheit. Standing there, exposed, a human would die in minutes. That is the limit of cold our planet can produce. The moon laughs at that number. During the 2-week lunar night, the surface can plunge toward 300 degrees below 0 Fahrenheit. In the deepest shadows near the poles, it drops even further, colder than the surface of Pluto, that frozen dwarf world at the far edge of our solar system. The Moon, our bright and friendly neighbour, hides some of the coldest ground anywhere near us. Why does it get so brutally cold? Blame the missing air again. On Earth, air acts like a blanket. When the sun sets, that blanket holds the day's warmth close to the ground, so the temperature falls slowly and gently. The Moon has no blanket. The moment the sun vanishes, all the heat rushes straight out into space with nothing to hold it back. The ground dumps its warmth in hours and keeps falling for 2 full weeks. Cold like that does more than sting, it destroys. Metal grows brittle in deep cold. Bend it and it snaps like a dry twig instead of flexing. Rubber seals harden and crack. Batteries lose their power and can freeze solid. Electronics stop working when their tiny parts get too cold to move electricity properly. Nearly every machine humans build has a temperature where it simply quits, and the lunar night blows straight past it. We have already watched this happen. A small Japanese lander touched down on the Moon and did its job in the sunlight. Then night came. The craft was never built to survive it. Engineers powered it down and hoped. Against the odds, it woke up again when the sun returned, then survived several more freezing nights before finally going silent. Every survival was a small miracle, and every night the machine had to shut itself off and gamble that it would ever turn back on. That is the cruel choice the cold forces. A base cannot simply shut down and sleep for 2 weeks. People live there. They need heat. They need air moving. They need water that stays liquid and food that stays safe. All of that takes power, and it takes it around the clock, through the entire 2-week night, while the temperature outside sits colder than Pluto. Picture keeping a house warm through a winter that lasts 2 weeks with no sun at all, in a place where stepping outside means instant killing frost, and where the nearest hardware store is 250,000 miles away. If the heat fails, there is no neighbour to call, no rescue that arrives in time. The cold moves in within hours. The metal of the base itself would fight you. As it swings from boiling day to freezing night and back again, it expands and shrinks, over and over, every month. Engineers call this thermal stress. It is like bending a paperclip back and forth. Do it enough times, and even strong metal grows tired, weakens and breaks. So the base must hold its warmth against the deepest cold in the neighbourhood for 2 weeks straight, without the sun's help. Which raises the question that has haunted every moon plan ever drawn. If solar panels die the moment the sun sets, what on the Moon is going to keep everyone alive in the dark? Sunlight in space is a gift. Above the Moon's surface, with no clouds and no air to dim it, the sun pours down stronger and steadier than anywhere on Earth. Solar panels love it. During the long lunar day, they can drink in that light and run a whole base with ease. Then the sun sets, and the gift is taken away for 2 weeks. This is the power trap at the heart of every moon base plan. The cleanest, simplest, cheapest way to make electricity on the Moon works perfectly for half the month, and then delivers nothing for the other half. And the half where it fails is the half where the base needs power most, because that is when the killing cold arrives. So the panels alone cannot save you. You need a way to store 2 weeks of power, or make it fresh in the dark. Storing it sounds easy until you look at the numbers. A base needs a huge amount of energy to keep people warm, to recycle their air, to melt their water, to run every machine. To hold 2 full weeks of that energy, you would need a mountain of batteries. And batteries are heavy. Every pound sent to the Moon costs a fortune to launch, and the batteries themselves hate the cold, losing power exactly when you need them, and risking freezing solid. Imagine trying to power your entire home for 14 days straight, on nothing but batteries, with no way to plug into the grid, and with the batteries stored outside in the worst cold on the planet. That is the storage problem, and it only grows as the base grows, so most serious plans give up on batteries as the main answer, and reach for something bolder. They reach for nuclear power. A small nuclear reactor makes its own heat and its own electricity, with no help from the sun. It runs in daylight and darkness alike. It shrugs off the 2-week night. Drop one at a base, and, in theory, you have steady power forever. Through every long night the Moon can throw at you. That is why space agencies are now racing to build tiny reactors made to sit on the lunar surface. On paper, it is the perfect fix. In reality, it opens a whole new box of dangers. A reactor is complicated. It has moving parts and hot cores and cooling systems, all of which must work flawlessly 250,000 miles from the nearest repair crew. It must survive the launch, the landing, and the same brutal dust and cold that threaten everything else. If it breaks in the dark, the base freezes with it. There is also the simple problem of getting it there. A reactor is heavy and delicate and, understandably, something people are cautious about strapping to the top of a rocket. Building one small enough to fly, safe enough to launch, and tough enough to survive the moon has taken years, and it is still being worked out. The power problem is a wall that every moon base slams into. Sunlight abandons you for 2 weeks. Batteries are too heavy and hate the cold. Nuclear might work, and it is hard, slow, and risky. And that word nuclear carries dangers of its own. Because putting a reactor on the moon means facing risks that go far beyond a dead battery. The plan sounds like science fiction. Build a nuclear reactor small enough to fit on a rocket, launch it off the Earth, land it gently on the moon, and let it hum away for years, feeding a base with power the sun cannot provide. Space agencies are dead serious about this. It may be the only way to survive the 2-week night, but every step of the plan carries a danger that would make any engineer sweat. Start with the launch. A rocket is basically a controlled explosion pointed at the sky. Rockets fail. They blow up on the pad, they tumble out of control and are destroyed on purpose to keep them from crashing into cities. Now imagine strapping a nuclear reactor to the top of one. Engineers have to design it so that even if the rocket explodes, the nuclear material stays sealed and safe, and never rains down over the ground below. That is a fearsome thing to promise. Say the launch works. Now the reactor has to land on the moon. Landing is one of the hardest, deadliest parts of any moon mission. Machine after machine has crashed trying to touch down, tipping over, slamming too hard, or losing control in the final seconds. A crashed reactor is far worse than a crashed lander. It could scatter its core across the very ground where astronauts are meant to live. Say the landing works too. Now the reactor has to run, untouched, for years, on a world coated in electric glass dust and swinging from boiling heat to Pluto cold. A reactor needs to shed heat to stay stable, and shedding heat on the airless moon is its own hard problem. It needs cooling systems and moving parts, all of which must survive the dust that jams everything and the cold that cracks everything. And if something goes wrong, there is no fire department, no repair van, no engineer who can drive over that afternoon. The nearest human help is 250,000 miles away, days from arriving even in the best case. Here is a way to feel the weight of it. Building a nuclear reactor on Earth already takes armies of experts, mountains of safety rules, and years of careful work, and that is with the reactor sitting still on solid ground with rescue crews nearby. Now do all of that, but first shake it violently on a rocket, drop it onto another world and walk away, trusting it to run alone in the harshest place humans have ever tried to tame. There is a reason this has never been done at full scale. The first surface reactors are still being designed and tested, and their target dates keep slipping, the same way every moon deadline slips. Some plans hope for a working reactor on the moon by the early years of the next decade. Hope is doing a lot of work in that sentence. Even a small reactor only makes enough power for a small base. Grow the base, add more people, more machines, more greenhouses, and you need more reactors, each one another gamble on launch, landing, and survival. So the power that keeps a moon base alive rests on one of the most complicated and nerve-wracking machines humans build, flown to the worst possible place to operate it. Yet power is only about keeping the lights on. There is a threat on the moon that reactors cannot stop, a threat that pours down from the sky and passes straight through walls. Radiation is already falling on the surface, and there is nothing up there to shield you from it. Earth is wrapped in an invisible force field, and most people never think about it. Deep inside our planet, molten metal churns and spins, and that motion creates a vast magnetic field that reaches far out into space. It is called the magnetosphere, and it is one of the main reasons you are alive. Space is full of radiation. Fast, invisible particles come screaming in from the sun and from distant exploded stars, moving at nearly the speed of light. This radiation can tear through living cells and damage the DNA inside them. On Earth, the magnetic field catches most of these particles and steers them away, like a shield deflecting arrows. On top of that, our thick air soaks up much of what gets through. The Moon has neither of these guards. Its metal core cooled and slowed long ago, so it has almost no magnetic field, and it has almost no air, so the radiation from space hits the lunar surface head-on, full strength, with nothing to soften the blow. Every astronaut standing on the Moon is standing in that rain of particles exposed. There are two kinds of danger falling from the black sky. The first comes steadily, all the time. It is made of high-energy particles from deep space, born in the violent deaths of far-off stars. They arrive quietly, constantly, day and night, and they are frighteningly hard to stop. They can punch clean through the metal walls of a spacecraft and through a human body. Over time, this steady dose adds up. It raises the risk of cancer. It may harm the heart and blood vessels. Scientists worry it could even damage the brain slowly, particle by particle, over months and years of exposure. On the space station, astronauts get some protection because they still sit inside the edge of Earth's magnetic shield. On the Moon, that shield is gone. Picture standing outside in a strange rain, except the raindrops pass straight through your umbrella, through your coat, through your skin, leaving tiny tears in your cells with each one. You feel nothing, you see nothing, and that is what makes it so frightening. The damage builds silently, with no pain to warn you and no way to wipe it off. This is why the beautiful drawings of glass domes on the Moon are a fantasy. A clear dome would let the radiation pour right in. To truly protect people, a base has to be shielded by something thick and heavy, thick enough to absorb the particles before they reach human bodies. On Earth, our air and magnetic field do that work for free. On the Moon, we have to build the shield ourselves, out of whatever we can find. And there is more than one way this radiation can kill. The steady background rain is only the slow danger. There is a second kind, far more sudden, far more violent, that can arrive with almost no warning. The sun itself can turn into a weapon. Every so often our star erupts, hurling a storm of radiation across space. On Earth, we barely notice because our shield absorbs the blow. On the Moon, an astronaut caught in the open during one of these storms would be in mortal danger within hours, and the sun does not send a warning letter before it fires. The sun looks calm and steady from Earth. It is a seething, violent ball of fire, and now and then it loses its temper. When that happens, the sun blasts out a huge burst of radiation and charged particles, a solar storm racing across space at incredible speed. These storms are real, common, and powerful. They have knocked out power grids on Earth, they have scrambled satellites, and they carry enough radiation to be deadly to anyone caught unprotected in space. On Earth, we ride these storms out safely. Our magnetic shield and thick air absorb the worst of it. We might see beautiful glowing lights in the sky, and maybe a radio crackles, but our bodies stay safe. On the Moon, with no shield and no air, a strong solar storm becomes one of the most dangerous events an astronaut can face. Here is the terrifying part. During a bad storm, an astronaut standing on the open lunar surface could soak up a dangerous dose of radiation in just hours. In the very worst storms, that dose could be enough to cause serious radiation sickness, or worse, in a single afternoon. We got lucky once, and few people know the story. Back in the Apollo years, between two of the crewed moon missions, the sun let loose one of the most powerful storms of the century. The radiation that swept past the Moon during that storm was fierce enough that, had astronauts been out on the surface, they could have been gravely hurt. The timing was pure chance. The storm arrived while no one was there. We rolled the dice and won. A permanent base cannot count on luck like that. If people live on the Moon for years, sooner or later a big storm will come while they are there. The question is whether they can get to safety in time, and time is the cruel twist. These storms travel fast. The warning we get can be short, sometimes only a matter of hours, sometimes less. An astronaut a long way from shelter, out exploring or repairing equipment, might not make it back before the worst of the radiation hits. Think of it like a tornado that you cannot see coming until it is nearly on top of you, in a land with almost no basements to hide in. You would need a shelter close by at all times, a thick-walled safe room you could reach in minutes from anywhere you work. That means a real base needs a storm shelter, a heavily shielded room buried under rock or piled over soil, ready at a moment's notice. Every trip outside becomes a gamble on the sun's mood. Every astronaut has to stay within a short sprint of safety, always watching, always ready to run for cover. And building that safe room brings us back to the same brutal fact. To stop this radiation, you need mass. You need thick walls, heavy shielding, tons of material stacked between the crew and the sky. Hauling all that from Earth would cost a fortune, so the plan is to build it out of the moon's own dirt. Which sounds clever until you remember what the moon's dirt is made of. The same glass dust that ruins machines and scars lungs is now the very stuff we must pile up to survive. Even after we survive the storms, another invisible enemy keeps falling, and this one never pauses, hour after hour, year after year. The solar storms are the loud danger. There is a quieter one that never lets up, and in some ways it is the harder problem to solve. It comes from far outside our solar system, from the wreckage of stars that exploded long ago. Scientists call it galactic cosmic radiation. These are particles moving so fast, carrying so much energy, that stopping them is one of the great unsolved puzzles of space travel. Here is what makes them so stubborn. With normal radiation, you can just add a thicker wall. More metal, more concrete, more shielding, and less gets through. Cosmic rays break that rule in a nasty way. When one of these superfast particles slams into a wall, it can shatter atoms inside the wall itself and spray out a shower of new particles on the other side. So a thin shield can actually make things worse, turning one dangerous ray into many. To truly block them, you need a wall that is enormously thick. Feet upon feet of solid rock or soil. The shielding that would keep a crew safe for years could weigh more than the entire rest of the base combined. This is the wall that no rocket can carry. Launching that much mass from Earth would cost sums so huge they break every budget. So there is only one real answer. Build the shield out of the moon. The plan is to bury the base, or to pile moon dirt over it in a thick blanket, feet deep, until the crew is wrapped in enough rock to soak up the rays. The moon has endless dirt and it is already there, so in theory it is free. You just have to move mountains of it. That means digging. Endless digging, in the worst possible soil, with machines that the glass dust is trying to destroy. It means either burrowing underground or building thick walls and heaping soil on top, one scoop at a time, using heavy equipment that has to survive everything the moon throws at it. Think of it like trying to build a bunker while standing inside a sandstorm made of powdered glass, on a world where every tool you own is slowly grinding itself to death. And even a buried base leaves a gap. The moment astronauts step outside to explore, to mine, to fix a broken reactor, they leave the shield behind. Out on the surface, the cosmic rays fall on them again, adding to a dose that builds across their whole stay. The longer they live on the moon, the more radiation their bodies collect, and the higher their lifetime risk of cancer and other harm climbs. On Earth, we spend our whole lives under a shield we never think about. The moon strips that shield away and hands us the job of rebuilding it by hand, out of the very dust that fights us at every turn. So the radiation problem is bigger than a single wall. It shapes everything: where you build, how deep you dig, how long a person can safely stay, how far they can wander from shelter, and we have only counted the dangers that come from outside the body. The moon has a way of attacking from within, of turning the human body against itself, using a force so gentle you can barely feel it. That force is gravity, or rather, the strange lack of it. Step onto the moon and you would feel like a superhero. Your body weighs only 1/6 of what it weighs on Earth. A person who weighs 120 pounds here would weigh about 20 pounds there. You could leap over a car. You could carry loads that would crush you at home. The Apollo astronauts bounced across the surface like happy kangaroos. That lightness feels like a gift. Over time, it becomes a slow curse. Your body is a machine built for Earth's pull. Every day of your life, gravity tugs down on you, and your body pushes back to stay strong. Your bones stay dense because they carry your weight. Your muscles stay firm because they fight gravity with every step. Your heart stays powerful because it pumps blood up against the downward pull. Take most of that pull away, and your body notices fast. It decides it no longer needs all that strength. So it begins to let go. Bones are the scariest part. In low gravity, they thin out. The body pulls minerals out of them because it decides they are no longer needed to hold up your weight. Astronauts on the space station can lose a frightening amount of bone every month, far faster than an elderly person losing bone on Earth. Thin bones snap easily. A fall that would only bruise you at home could shatter a bone on the moon, and there is no hospital waiting. Muscles fade too. Without the constant work of fighting gravity, they shrink and weaken. The heart, which is a muscle, can grow weaker and change shape. Even after just months in low gravity, astronauts come home so weak they can barely stand, and they need long, hard rehab to walk normally again. On the space station, astronauts fight back with brutal exercise. They strap themselves to machines and work out around 2 hours every single day, just to slow the damage. And here is the catch. The moon is a different world from the space station. The exercise machines that work in the weightless station may fail in the moon's 1/6 gravity, where your feet still touch a floor but only barely press against it. Scientists are still figuring out how to keep a body strong in this strange in-between world. There is a deeper worry hiding underneath all this. On the space station, no one stays forever. Astronauts go up, spend a few months, and come home to heal. A permanent moon base is different. The whole point is to stay for a long time, maybe years. Nobody knows what years in 1/6 gravity would do to a human body. We have never done it. Would bones keep thinning until they crumble? Would muscles waste past the point of recovery? Could a person who spent years on the moon ever safely return to Earth's full gravity? Or would the trip home crush them? These are open questions, and the only way to answer them for certain is to risk human bodies finding out. Picture a plant grown in a room with almost no gravity to pull against. It grows thin, pale, and weak, unready for the real world outside. A human body in low gravity drifts the same way, softening in the very ways that once kept it alive, and bones and muscles are only the visible damage. The gravity change reaches somewhere far more delicate, somewhere that could steal an astronaut's sight. It is coming for the eyes. On Earth, gravity is always pulling your blood and body fluids down toward your feet. Your heart works against it, pumping everything back up. Your whole system is balanced around that constant downward tug. Take gravity away, and the balance breaks in a way few people expect. Without a strong pull toward your feet, fluids drift upward and pool in your head and chest. Astronauts call it the puffy face. Their cheeks swell, their heads feel stuffed and heavy, like a bad cold that never clears. Their legs grow thin as the fluid abandons them. It looks almost comical in photos. Inside the body, it is doing something serious. All that extra fluid raises the pressure inside the skull, and that pressure pushes on a place that cannot afford it, the back of the eye. Doctors have found that many astronauts come home with changed eyesight. The pressure squeezes and flattens the back of the eyeball. It swells the nerve that carries sight from the eye to the brain. Some astronauts return needing glasses they never needed before. The vision change can linger long after they land, and doctors are still learning whether it ever fully heals. They gave this problem a long name, but the plain version is simple. Space is squeezing astronauts' eyes from the inside, and it may be slowly stealing their sharp vision. Now think about what that means for a moon base. The moon has some gravity, about 1/6 of Earth's, so the fluid shift may be gentler than in the weightless space station. It may be. Nobody knows for sure, because nobody has ever lived in 1/6 gravity for a long time. The moon sits in an unknown middle zone, and we are guessing at what it does to the human body. If the pressure builds even slowly over months and years, an astronaut could watch their own eyesight fade while they live there. On a world where survival depends on reading instruments, spotting hazards in that knife-edge shadow, and doing delicate repairs, fading vision is more than an inconvenience. It could be deadly. And the eyes are just one soft target. The same fluid shift changes how blood reaches the brain. It may affect the heart, the pressure in blood vessels, even the way the body delivers oxygen to the places that need it. Scientists studying this describe the body as one connected system, where a change in gravity ripples through everything at once in ways they are only beginning to map. Here is the humbling truth. We evolved over millions of years under Earth's exact pull. Every part of us, from our bones to our blood to the fluid behind our eyes, is tuned to that one number. Change the number and the body starts to drift out of tune. silently, in a dozen ways at once. Picture a delicate instrument, perfectly calibrated for one setting, then move somewhere the rules are different. It keeps playing, but every note bends slightly wrong, and the longer it stays, the further out of tune it slides. A moon base is meant to hold humans for years, yet the longer they stay, the more their bodies bend away from the shape that keeps them alive. Bones thin, muscles fade, eyes blur, and we still do not know where it stops. The moon is telling us something harsh. Its surface may simply be too hostile for human bodies to endure for long, which is why the boldest plans have stopped trying to live on the surface at all. They want to go underground. By now, the surface of the moon looks like a death trap. Glass dust that ruins machines and scars lungs. A night that lasts 2 weeks and freezes everything. Radiation pouring from the sky. Solar storms that strike with little warning. Space rocks falling like bullets. Gravity so weak it wastes the body away. Faced with all of that, engineers reached a bold conclusion. To survive, we may have to stop living on the moon and start living inside it. The idea is to bury the base. Go underground, where the moon's own rock becomes a shield against nearly every danger above. It makes a strange kind of sense. Just a few feet of rock and soil overhead would block most of the deadly radiation, the same radiation that no thin wall can stop. Underground, there are no solar storms to fear, because the rock soaks them up. There are no falling space rocks, because the ceiling catches them. And here is the quiet miracle. Deep enough down, the wild temperature swings vanish. Remember the surface, boiling for 2 weeks, then freezing for 2 weeks. Rock is a good insulator. Go far enough below the surface, and the temperature stops swinging and settles at one steady cold value that barely changes at all. Cold, yes, and steady. And steady is something engineers can work with. Steady means an end to the brutal expanding and shrinking that cracks metal apart every month. So underground, 4 of the moon's worst weapons lose their power at once. Radiation, storms, falling rocks, and the killing temperature swings all fade away behind a wall of stone. Picture the difference like this. On the surface, a base is a tent in the middle of a battlefield, hit from every side. Underground, it becomes a bunker carved into bedrock, with the whole moon standing guard above it. There is even a bonus. Down in the rock, the base can be roomier and safer. Instead of squeezing everyone into a tiny metal can piled high with heavy shielding, you let the moon do the shielding for free and build living space in the shelter it provides. This is why serious plans have shifted their dreams downward. The glowing surface domes make pretty pictures, and the people who study this hardest keep pointing at the ground and saying the real future is below it. But burying a base raises a giant question. How do you get underground in the first place? You have 2 hard choices. You can dig your own hole, which means bringing heavy digging machines to the moon and running them in the glass dust that destroys everything, scooping out tons of rock a little at a time. Slow, brutal, and expensive. Or you can find a hole that already exists, and it turns out the moon may have exactly that. Hidden beneath its surface, scientists believe there are giant natural caves, tunnels left over from an ancient, violent past when the moon still burned. Some may be enormous, big enough to swallow entire buildings, maybe even whole towns. If those caves are real and safe, they could be the ready-made homes that make a permanent base possible. No digging required, just move in. There is only one problem with that dream. No human has ever set foot inside one. We're not even sure they will hold. Billions of years ago, the moon was a very different place. It burned. Rivers of molten rock flowed across its surface and poured beneath it. When those rivers of lava drained away, they left something behind. Empty tunnels. Long, hollow tubes carved through the rock where the lava used to run. We have the same thing on Earth, in volcanic places like Hawaii and Iceland. They are called lava tubes, and people walk through them all the time. On the moon, they may be vastly bigger. Here is why. The moon's gravity is weak, only 1/6 of Earth's. Weaker gravity means a roof of rock can span a far wider gap before it caves in. So lunar lava tubes could be giants compared to ours. Scientists studying the data believe some may be wide enough and tall enough to hold entire buildings inside them. A few estimates suggest the largest could fit a small city under a single stone roof. Think about that. A natural cavern beneath the moon, big enough to build a town inside with a ceiling of solid rock already blocking the radiation, the storms, the falling debris, and the temperature swings. It would be the perfect shelter, and the moon made it for free. We know these openings are real because we have seen their doorways. Cameras orbiting the moon have spotted deep pits in the surface, dark holes punched into the ground. Scientists believe many of these pits are skylights, places where the roof of a lava tube collapsed long ago, opening a window down into the cave below. Peer into one and you see darkness, and a hint of a floor far beneath, and the edge of a tunnel running off sideways into black. Recent studies have gone further. By bouncing radar off the moon, scientists found strong evidence that at least one of these pits really does open into a long cave stretching underground, exactly as hoped. The dream is turning out to have real stone behind it. Picture standing at the edge of one of these pits in your spacesuit. Below you yawns a hole dozens of feet deep, leading into a tunnel older than life on Earth, untouched, unseen, waiting in perfect darkness for the first visitor in billions of years. Inside, the temperature holds steady. The radiation cannot reach you. It might be the single safest spot for a human anywhere off the Earth. This is why the caves have set imaginations on fire. A permanent base inside a lava tube would solve so many problems at once. It would shield the crew from nearly everything the surface throws at them. It would give them room to grow. It would let them build without hauling tons of heavy shielding across space, because the moon's own rock is already the shield. Some scientists even dream of sealing off a section of a tube, filling it with air, and turning it into a giant underground room where people could one day walk without a suit, safe beneath the ancient stone. It sounds like the answer to everything. A ready-made home, hidden and waiting, that could finally make living on the moon possible. And yet, for all the excitement, one enormous unknown hangs over the whole beautiful idea. We have never gone in. Every hope rests on caves no human or machine has ever entered, and there are good reasons to be afraid of what happens when we finally do. Every plan to live inside a lunar cave shares one giant weakness. It is built entirely on hope. No person has ever gone inside one. No robot has either. We have peered down through the skylights from above and bounced radar off the rock, but the caves themselves remain a total mystery. And a mystery is a dangerous thing to bet your life on. Start with the most basic fear. Will the roof hold? These tunnels are billions of years old. The rock has been baked, frozen and shaken for longer than the Earth has had oceans. We believe the low gravity lets the ceiling span wide gaps, but believing is a long way from knowing. Move a base inside, and you're trusting an ancient stone roof to hold above your head forever. If any part of it gives way, there is no escape from a collapse underground. Then there is the problem of simply getting in. The doorways are collapsed pits, some dozens of feet deep, with steep or sheer walls. You cannot drive a rover down a cliff. Astronauts would have to climb down into the dark, lowering themselves and their heavy equipment into a hole, then find a way to haul everything back up again. Every trip in and out becomes a climb into a pit, in bulky suits, in low gravity, with glass dust coating every rope and handhold. Inside, we have no idea what waits. The floor could be smooth, or it could be a jumble of collapsed boulders impossible to build on. The cave could be a clean tunnel, or a maze of dead ends and drops. There could be loose rock ready to fall. There could be cracks that leak away any air you try to pump in. We are guessing at all of it from a few blurry images taken from orbit, and remember the dust. Even underground, the moon's glass powder is everywhere, coating the floors of these caves too. Climbing in and out would stir it up in the dark, where it clings to everything and floats in the still air with nowhere to settle. Picture being told there is a perfect house for you, but it sits at the bottom of a pit you have never climbed into, in total darkness, and no one has ever checked whether the ceiling is about to fall. You would want to send something to look first. You would want to be very, very sure before you moved your family in. That is exactly where we stand. Before anyone can live in a lunar cave, we have to send robots down to explore them, map them, test the rock, and prove they are safe. That mission has never flown. It is hard because a robot has to survive the climb down, work in the dark, and crawl through terrain no one has mapped. Building such an explorer is a challenge all its own, and it has to succeed before the real dream can even begin. So the caves are a promise, glowing and beautiful and completely unproven. They might be the salvation of the whole moon base dream. They might turn out to be death traps of falling rock and leaking walls. Right now, honestly, we do not know which, and even if the caves are perfect, and even if we build the safest shelter imaginable, we still have to do the one thing the moon fights hardest against. We have to dig. And digging on the moon may be the hardest construction job ever attempted. Whether we bury a base or move into a cave, the moon demands the same brutal task. We have to move rock. We have to dig, scrape, haul and build using heavy machines on a world that seems designed to destroy them. On Earth, digging is routine. Bulldozers and drills tear through ground every day. We rarely think about how much those machines depend on the gentle world around them. Air to cool their engines, grease and oil that stay liquid. Ground that pushes back when they push against it. Repair shops down the road when something breaks. The moon strips all of that away and adds a new enemy on top. Start with the dust because it never stops causing trouble. We have seen how the moon's glass powder grinds down seals and clogs joints. Now imagine running a digging machine right in the heart of it, deliberately churning up clouds of the stuff hour after hour. Every scoop throws more razor grains into every moving part. The very act of digging surrounds the machine in the one thing most likely to kill it. Drills would dull and jam. Gears would grind themselves apart. Moving parts would seize. Then there is the weak gravity, which sounds helpful and works against you. On Earth, a heavy machine can push hard into the ground because its own weight holds it down. On the moon, everything weighs 1/6 as much, including the digger. Try to push into the rock and the machine just skitters and bounces backward, with too little weight to hold it steady. Digging becomes like trying to shovel while floating in a swimming pool. You push and you drift away instead of the dirt. Cooling is another silent problem. Machines make heat when they work. On Earth, air carries that heat away. The moon has no air, so heat has nowhere to go and builds up inside the machine until parts overheat and fail. Engineers have to design special ways to dump that heat into empty space, which is slow and difficult. And every one of these machines has to survive the same lunar night that threatens the base, freezing for 2 weeks toward Pluto cold, then baking in the 2-week day. Metal that must dig also must endure that swing over and over without cracking. Now stack on the distance. If a digger breaks on Earth, a mechanic fixes it that afternoon. If a digger breaks on the moon, the nearest mechanic is 250,000 miles away, and spare parts have to be launched on a rocket months in advance. So the machines must run almost perfectly, alone, in the harshest conditions imaginable, with no one to save them when they falter. Picture trying to build a basement using power tools that are slowly filling with broken glass, that keep floating off the ground when you push them, that overheat because there is no air, and that freeze solid every couple of weeks, all while the nearest hardware store is farther than any store has ever been. This is why building anything on the moon is so slow and so costly. Each scoop of rock is a fight. Each machine is a gamble, and a base needs a lot of scoops, tons upon tons of rock moved, just to bury the crew deep enough to keep them alive. Yet even a buried, shielded, dust-proof base still needs the things every living thing needs. It needs water. And on the moon, the water hides in the darkest, coldest, cruelest places of all. A base needs water. People drink it. Plants need it. And water can be split apart into oxygen to breathe and hydrogen for fuel. Water may be the single most valuable thing on the moon. For a long time, people thought the moon was bone dry. It turned out we were looking in the wrong places. The water is there, but it hides in the strangest, most forbidding spots imaginable. It hides in the bottoms of craters near the moon's poles, in places where sunlight has never reached, not once, in billions of years. Here is how such a place can exist. Near the moon's poles, the sun always hangs low, skimming along the horizon. It never climbs high overhead, so the floors of deep craters down there sit in permanent shadow. The crater walls block the low sun forever, and the bottom stays dark for all of time. Scientists call these permanently shadowed regions. They are among the darkest, oldest, most untouched places in the entire solar system, and because the sun never warms them, they are unimaginably cold. These crater floors can drop to around 400 degrees below 0 Fahrenheit. That is colder than the surface of Pluto. It may be among the coldest natural spots anywhere in our whole solar system, and it sits right here on the moon we see glowing in our sky every night. That killing cold is exactly why the water survives. Over billions of years, comets and space rocks carrying ice crashed into the moon. Almost everywhere, the sun's heat boiled that water away into space. But in these frozen shadow traps, the cold locked it in place. The ice fell in, and it stayed. It has been waiting in the dark ever since, a hidden treasure at the bottom of the coldest pits on the moon. We are fairly sure it is there. Years ago, scientists deliberately crashed a rocket stage into one of these dark craters and watched the plume of debris it kicked up. In that plume, instruments detected the signature of water ice. The moon had been hiding a frozen reservoir in its darkest corner all along. This is the reason the whole world suddenly wants the moon's south pole. That is where these shadowed craters cluster, and that is where the ice is richest. Every nation planning a base is aiming for the same small region, drawn by the promise of water frozen in the dark, because water changes everything. If you can dig up lunar ice, you can drink it. You can breathe the oxygen inside it. You can even make rocket fuel from it, which means a moon base could refuel ships without hauling every drop from Earth. Water is the key that could unlock the whole dream of living in space. Picture the most precious well in the world, except it sits at the bottom of a pit that has been in total darkness since before the first fish crawled onto land, in a cold so deep it freezes the air itself. That is where the moon keeps its treasure. And that is the cruel joke. The one resource that could make a moon base possible is buried in the one place almost impossible to work. To reach the water, astronauts and machines have to go down into the coldest, darkest holes in the solar system and try to mine there. And mining in a place that cold breaks rules we have never had to break before. Finding the ice was the good news. Getting it out is a nightmare that pushes machines past their breaking point. Start with the cold. The floors of these shadowed craters sit at around 400 degrees below 0 Fahrenheit. At temperatures that low, ordinary rules stop working. Metals turn brittle and can shatter. Ordinary batteries die. Lubricants freeze into useless sludge. Electronics stop functioning because their tiny parts cannot move electricity in such deep cold. A machine that works fine in the 2-week lunar day might simply freeze solid the moment it rolls into one of these pits. Now add the darkness. The whole reason the ice survives is that sunlight never touches these craters. But that same darkness means solar panels are worthless down there. There is no sun to catch, ever, so any machine mining the ice has to carry its own power source into the pit and keep itself warm enough to function, while sitting in a cold that is actively trying to freeze it to death. It has to fight the temperature and do its job at the same time. Then think about the ice itself. The lunar ice hides as frozen grains locked inside the frozen ground, mixed through the rock and dust. In that deep cold, the icy soil can be as hard as concrete. Digging it out means grinding through frozen rock with machines already struggling to survive the temperature, in the dark, in the glass dust, far from any help. And once you free the ice, you have to capture it before it escapes. On the airless moon, ice does something sneaky. Warm it even a little and it leaps straight from solid to vapor, skipping the puddle stage entirely, and vanishes into space. So a miner cannot just scoop up ice and carry it home. It has to trap the vapor the instant it forms, sealing it before the vacuum steals it away. That is a delicate trick to pull off in the harshest conditions imaginable. Picture trying to dig frozen treasure out of concrete, in total darkness, in a cold deep enough to shatter steel, using machines that must generate their own light, their own heat, and their own power, while a vacuum tries to snatch away every bit of treasure the moment you free it. And you must do it 250,000 miles from the nearest spare part. We have never done anything close to this. Robots have crashed just trying to land near these regions. Landing inside a permanently shadowed crater, in the dark, on unknown terrain, is one of the hardest targets in all of space travel. Working there, day after day, mining tons of ice, is a challenge that lives mostly in drawings and hopes right now. Here is the trap at the center of it. A moon base needs water to survive long term. The water is real, and it could change everything. But it sits in the one environment that our machines find nearly impossible to endure. The prize and the punishment are the same place. So even the moon's greatest gift comes wrapped in cruelty. The water that could make a base self-sufficient is locked in the coldest, darkest vault in the solar system, guarded by a coal that breaks everything we send to open it. And suppose we crack that vault. Suppose we haul the ice up into the light. Then comes the dream that has driven this whole effort. The dream of turning that ice into fuel. It is a beautiful idea. It is also far harder than the brochures admit. Here is the vision that excites everyone. Mine the ice. Split it apart. Water is made of hydrogen and oxygen, and both are rocket fuel. Do this on the moon, and you could fill up spaceships without launching a single drop from Earth. A moon base could become a cosmic gas station, refueling ships headed deeper into space. It is a gorgeous idea. It could change the future of space travel, and it runs into a wall of hard, stubborn reality. Splitting water sounds simple, and in a lab it is. Run electricity through water, and it separates into hydrogen gas and oxygen gas. School children do it in science class. The trouble is doing it on the moon, at a scale big enough to fuel real rockets, in the middle of everything else the moon throws at you. Start with the electricity. Splitting water takes a lot of power. Splitting enough water to fuel a rocket takes an enormous amount. Remember the power problem from earlier, the 2 week nights, the heavy batteries, the risky reactors. Now you need even more power, piles of it, just to make fuel. Every drop of rocket fuel you create demands a mountain of energy first. Then there is the sheer amount of ice you would need. Rockets are thirsty. Filling one takes tons of fuel, which means splitting tons of water, which means mining tons of ice out of those frozen pitch-black craters. The mining that we just saw is nearly impossible, would have to run at a huge scale, all day, every day, for the fuel dream to work. And hydrogen, once you make it, is a slippery, difficult thing to keep. It is the lightest stuff in the universe, and it loves to leak. It seeps through tiny gaps that would hold any other gas. To store it as liquid fuel, you have to keep it colder than almost anything and stop it from escaping, on a world that swings from boiling to freezing every 2 weeks. Holding on to hydrogen is like trying to carry water in your cupped hands. Some of it always finds a way to slip through. Every step in this chain is hard. Mine the ice in killing cold and dark. Haul it out without losing it to vapor. Purify it. Power a huge machine to split it. Capture the gases. Cool them into liquid. Store them without leaks. Do all of it far from Earth, in the dust and the cold, with machines that keep breaking. A single weak link anywhere in that chain, and the fuel dream stalls. Picture a factory with a dozen delicate steps, where each step is one of the hardest things ever attempted, and all of them have to work together flawlessly in the most punishing place humans have ever tried to build. That is what making fuel on the moon really means. This is why the fuel dream, for all its power, keeps living in the future. Small experiments are planned. Little test machines will try to pull oxygen and water from lunar soil. But a full fuel factory, cranking out tons of rocket propellant on the moon, is still a distant hope, waiting on 100 smaller problems to be solved first. The promise is real. The payoff would be huge, and the road to it is longer and harder than the bright pictures ever show. So far, every danger has come from the moon's surface or its sky. But the moon has one more surprise, and this one comes from deep inside it. The ground itself hides a secret. The moon is shaking, and it is shaking right where we want to build. We think of the moon as a dead, frozen ball of rock, unchanging for billions of years. The truth is stranger. The moon is still changing right now, and the change is a violent one. The moon is shrinking. Deep inside, the moon is slowly cooling down. It has been losing its ancient heat for billions of years, and as its insides cool, they contract, the way a warm balloon shrinks a little when it cools. Over vast stretches of time, the whole moon has grown smaller, shrinking by more than 150 feet across its width. Here is the problem with a shrinking world. The outside cannot shrink smoothly. The moon's surface is a brittle crust of rock, and as the inside pulls in, that crust has too much skin for the smaller ball underneath. So it wrinkles and cracks. Think of a grape drying into a raisin. As it shrinks, its skin buckles into ridges and folds. The moon is doing the same thing, on a scale of miles. These cracks have a name: faults, All across the moon, the shrinking has pushed the crust until it broke, shoving slabs of rock over one another and leaving long cliffs and ridges called scarps. Cameras orbiting the moon have spotted thousands of them, fresh-looking cracks scattered over the surface, marks of a world still splitting apart. And when rock cracks and slabs slip, the ground shakes. The moon has earthquakes of its own. Scientists call them moonquakes. We know moonquakes are real because the Apollo astronauts left instruments on the moon to listen for them. Those instruments recorded quakes for years. Most were gentle, but some were strong, and a few were surprisingly powerful, strong enough to shake the ground hard if you were standing on it. The scariest kind are the shallow moonquakes, the ones that happen near the surface where the faults are slipping. On Earth, our planet's quakes usually rumble and fade fast, partly because our wet, layered ground soaks up the shaking. The moon is dry and stiff, and it rings like a struck bell. Apollo scientists were stunned to find that some moonquakes made the moon vibrate for a shockingly long time, shaking on and on for many minutes, far longer than a quake on Earth. Imagine an earthquake that refuses to stop, that keeps trembling for longer than you can hold your breath, again and again. Now imagine your fragile base sitting on top of it, every seal and joint and wall being rattled, in a place where a single crack in the wrong spot lets your air rush out into space. For a short visit, a moonquake is a curiosity. For a permanent base meant to stand for years, it becomes a real threat. Buildings on Earth are designed to survive quakes, and that takes careful engineering. A moon base would need the same, on a world whose shaking we barely understand, using instruments we have yet to place to map where the danger is worst. Because here is the part that turns a curiosity into a warning. When scientists looked at where these quakes and cracks appear, they found something that should give every moon base plan a pause. The shaking is strongest at the very place the whole world is racing to build. Every space agency is aiming for the same tiny patch of the moon, the South Pole. That is where the shadowed craters hide their frozen water, and that is where nearly every base plane points. It is the most valuable real estate in the solar system, and it may also be one of the most dangerous. When scientists studied the moonquakes recorded long ago and traced the cracks scattered across the moon, they made an unsettling discovery. Some of the strongest shaking and many of the fresh active faults sit right in the south polar region. The exact area everyone wants to settle is also an area where the ground is cracking and quaking. One of the most powerful moonquakes ever recorded by the Apollo instruments came from near the South Pole. Its exact spot could not be pinned down precisely, but the cloud of possible locations spread across the very ground marked for future landings. Scientists looked at proposed landing zones and found young faults running right through some of them, faults that could still be active, faults that could still slip and shake. This is a serious warning, and it comes from careful study of real data. The people who found it said plainly that the location and stability of any permanent moon base needs to take these quakes into account. Build in the wrong spot on or near an active fault, and a base could one day face a strong quake tearing at its walls. Remember too how the moon rings. Its dry, stiff rock keeps shaking far longer than Earth's ground does. A quake that would pass in seconds here could tremble on for many minutes there. Minutes of relentless rattling working at every seal and joint of a base, in a place where a single breach lets the air rush out into the void. Picture a bell that keeps ringing long after it is struck. That is the moon's rock under a quake, humming and shivering on and on, while your fragile home stays fastened to its surface. This turns choosing a site into a life or death puzzle. You want to be near the water, which means near the poles. You want the high crater rims that catch near constant sunlight for power. But those same regions carry the active faults. The best spots for resources may be among the worst spots for safety, and we are still half blind. The old Apollo instruments gave us only a rough picture, from a handful of listening posts placed over 50 years ago. To really know where the ground is safe, we need new instruments spread across the moon, listening for quakes, mapping the danger. Those missions are only now being planned. Until they fly, every base site is chosen with incomplete knowledge, hoping the ground beneath it stays still. So the dream location, the prize everyone is chasing, comes with a hidden fault line running through it. The The moon is quietly warning us that the very ground we covet may be too restless to trust. But a shaking base is only the start of what these quakes can do. The real terror is what the shaking does to the steep slopes above the craters, the very slopes we must climb to reach the ice. Because when those slopes let go, everything on them comes down. The ice is at the bottom of craters, the steady sunlight is on the rims of craters, so a moon base near the pole will almost certainly sit on or near a slope, and slopes on a shaking moon are deadly. Scientists took the moonquakes they had found and asked a frightening question. What happens to the moon slopes when the ground shakes? They built models of the steep terrain near the South Pole and ran the tremors through them. The answer was alarming. Even light shaking could be enough to trigger landslides. Here is why the moon slopes are so touchy. For billions of years, loose rock and dust have piled up on those slopes, held in place only by the moon's weak gravity and their own delicate balance. Nothing ever disturbs them. No wind, no rain, no rivers. They just sit there, stacked and waiting, sometimes for longer than Earth has had complex life. It is a house of cards built over eons. Then a moonquake hits. The ground trembles, the delicate balance breaks, and all that loose material lets go at once. A landslide begins, sweeping down the slope, carrying rock and dust with it. In the moon's low gravity, that debris can travel a surprisingly long way, sliding and bouncing far across the surface before it finally settles. We have proof this happens. When scientists studied one of the old Apollo landing sites, they found the marks of past landslides and boulder falls, and they traced them back to moonquakes shaking the ground long ago. The moon has been quietly reshaping itself with these slides for ages. The evidence was sitting there in the rocks the astronauts walked past. Now put a base in the path of that. Imagine building your home partway up a slope to reach the sunlight, or down in a crater to reach the ice, and one day a quake shakes loose the hillside above you. There is no warning siren, there is no time to flee in a bulky suit across broken ground. The debris comes down, and if it strikes the base, it could crush a wall, bury an airlock, or tear the breach that lets your air pour out into space. Even a small slide could be a disaster. A base is a fragile bubble of air and warmth in a place that wants neither. It takes only a scattering of boulders, knocked loose by a tremor and striking the wrong spot to end everything inside. Think of the loose slopes like snow piled on a steep roof through a long winter, growing heavier and more precarious, waiting for one good shake to bring it all sliding down at once. The moon slopes have been loading up for billions of years, waiting for their shake. This forces base builders into another cruel trade-off. The resources pull you toward the slopes and the craters. The danger of landslides pushes you toward flat, open ground far from both. There may be no spot that is close to the water, bathed in sunlight and safe from sliding rock all at once. Every choice gives up something you badly need. The moon, it seems, guards its treasures with traps. The water is in the killing cold. The sunlight is on the shaking rims. The safe flat ground is far from everything useful. And even after you pick your careful, compromised spot, there is one more way to destroy a base, and this one arrives on a pillar of fire every time a ship comes to visit. A rocket landing on the moon looks graceful in the movies. A gentle descent, a soft touchdown, a little puff of dust. The reality is violent, and it creates one of the strangest dangers a base will ever face. When a rocket lands, it fires its engines downward to slow itself, blasting a powerful jet of exhaust straight at the ground. On Earth, the air spreads that blast out and softens it. On the moon, with no air, the raw force slams into the surface at full strength. And the surface, remember, is covered in that fine, sharp, glassy dust. The exhaust hits the dust and flings it outward in every direction. But here is the terrifying part. With no air to slow anything down, those grains rocket outward at incredible speed, some moving faster than a mile every second. That is faster than a bullet from a rifle. A landing spacecraft turns the ground beneath it into a giant spraying shotgun blast of glass moving at deadly speed. And in the vacuum, nothing stops those grains. On Earth, kick up dust and the air quickly brings it back down. On the moon, A grain launched sideways at a mile per second just keeps going, flying flat and far across the surface until it finally slams into whatever stands in its way. The dust from a single landing can spray across an area far larger than the landing spot itself. Now imagine that a base sits nearby. Every one of those high-speed grains is a tiny projectile. They sandblast anything they hit. They pit and scratch solar panels until they stop working. They scour windows into a frosted blur. They abrade seals, coat radiators, and hammer at the walls, each grain doing a little damage, and there are countless grains in every blast. We saw a hint of this back in the Apollo days. When one crew visited an old robotic probe that had been sitting on the moon, they found it sandblasted and coated, and worked out that a landing more than a football field away had done it. A distant touchdown had reached across the length of a soccer field to scour a machine with flying grit. Now scale that up to a big rocket landing again and again near a permanent base. Picture a sandstorm, except every grain of sand is a shard of glass moving faster than a bullet, and the storm erupts every single time a ship arrives or departs. That is what a rocket landing does on the airless moon. The bigger the rocket, the worse the blast. And a permanent base is visited by big ships, not tiny landers. It needs them to bring crew, cargo, fuel, and supplies over and over for years. Each arrival and each departure unleashes another storm of high-speed glass at whatever stands nearby. This is a problem with no easy answer. You cannot turn off a rocket's exhaust. You cannot make the dust heavier. As long as ships land on raw lunar dust near a base, that base gets sandblasted, its most delicate and vital systems worn down grain by grain. So the very thing that keeps a base alive, the steady stream of ships from Earth, is also a thing that could slowly destroy it. Which raises a strange and stubborn question that base planners are still wrestling with. If landing near your base can wreck it, then where exactly are all these ships supposed to land? The dust blast leads to a maddening puzzle. A base needs ships to survive. Ships bring the crew, the food, the fuel, the spare parts, everything. But every ship that lands sprays a storm of a high-speed glass across the ground. So the closer a ship lands to the base, the more it sandblasts and damages that base. The obvious answer is to land far away. Put the landing zone a safe distance from the base, so the flying dust settles before it reaches anything important. But that answer creates its own headache. If ships land far away, then everything they carry has to be moved across the surface to the base. Tons of cargo, heavy fuel, tired astronauts in bulky suits. All of it has to travel over rough, dusty, broken ground, hauled by rovers that the glass dust is already trying to destroy. Every delivery becomes a long, difficult journey across dangerous terrain, and the farther the safe landing zone sits, the harder that journey gets. So base planners are stuck between two bad options. Land close and wreck the base with dust. Land far and struggle to move everything across the moon. Both are painful, and there is no clean way out. The most promising idea is to build a landing pad, a hard, prepared surface for ships to land on, so they stop blasting loose dust every time. On Earth we land rockets on solid concrete which holds the ground in place. The dream is to build something similar on the moon, a smooth, tough pad that locks the dust down so touchdown stops spraying it everywhere. But building a landing pad on the moon is its own enormous project. You cannot ship slabs of concrete across space. So the plan is to make the pad out of the moon itself, melting or fusing the lunar dust into a solid surface, or somehow binding it into a hard crust that stays put. Doing that takes machines, power, and time, and it means construction work on the surface before the base can even open, in all the same dust and cold and danger we have already seen, and the pad has to be tough. Rocket landings are brutal, hitting the surface with fire and force again and again. A pad that cracks or crumbles under repeated landings is worse than useless. It has to be built strong enough to take a pounding for years, in a place where we have barely learned to build anything at all. Picture trying to pour a driveway strong enough to catch a falling rocket, using only the dirt already in your yard with no water, no cement truck, and tools that keep breaking, before you're even allowed to move into the house. That is the landing pad problem. Until it is solved, every ship that comes and goes is a fresh threat to the base it serves. The lifeline and the danger are the same rockets, and this is the pattern the moon keeps repeating. every solution births a new problem. Every gift comes wrapped in a threat. The dust, the cold, the dark, the radiation, the quakes, the blasts, they all tangle together into a knot that is fiendishly hard to cut. Yet suppose we cut it. Suppose we build the base, land the ships, bury the crew safe from the sky. They still have to eat. And feeding people on the moon runs into a wall as stubborn as any so far. The moon's own soil is toxic to the very plants we would need to survive. A base can be supplied from Earth for a while, but a truly permanent home cannot depend forever on food shipped across 250,000 miles of space. Sooner or later, the people on the moon need to grow their own food, and the moon fights that dream too. The obvious plan is to grow plants in the lunar soil, the way we grow crops in dirt on Earth. There is a serious problem with that. Lunar soil is a world apart from the rich Earth in a garden. It is that same ground-up glass and rock we have met again and again, and it is a hostile place for a living root. Real Earth soil is alive. It is full of tiny microbes, decayed plants, and nutrients that feed a growing crop. Lunar soil has none of that. It has never held life. It has no microbes, no decayed matter, nothing that a plant needs to grow. It is dead, sterile dust. Worse, it is chemically harsh. Lunar soil contains sharp glass and reactive chemicals, and it holds tiny bits of iron and other materials that can harm delicate roots. Scientists have tested growing plants in soil made to imitate the moon's, and the plants struggle. They grow slowly, sickly, and stunted, fighting for life in dirt that seems to reject them. There is an even nastier ingredient. Lunar soil can contain chemicals called perchlorates, and substances like these are toxic to people. The very ground the astronauts would try to farm could poison the crops, or the people who eat them, unless it is carefully cleaned first. So growing food in raw lunar soil is a losing battle. To make it work, you would have to treat the soil heavily, washing out the poisons, adding nutrients, bringing life to dead dust, all before a single seed could thrive. That is slow, delicate work, and it uses precious water and power the base can barely spare. Many plans skip the soil entirely and grow food without any dirt at all, feeding plants with water and nutrients in sealed indoor gardens lit by artificial light. That can work, and it avoids the toxic soil, but it demands enormous amounts of power to run the lights and pumps day and night through the long lunar darkness. Every lettuce leaf grown that way costs energy the base fought hard to make, and the whole garden is fragile. It lives inside the base, sharing its air and water. If the power fails during the 2-week night, the plants freeze. If the air system falters, they die. If a disease slips into that sealed indoor world, it can sweep through the whole crop with no open sky to save it. On Earth, a failed harvest means a trip to the store. On the moon, a failed harvest could mean slow starvation. Picture trying to run a farm inside a submarine, where every drop of water, every watt of light, and every breath of air has to be made by machine, and one broken pump could wipe out everything you planted. That is farming on the moon. Food, it turns out, is one more thing the moon refuses to give freely. Even the simple act of eating becomes a fight against dead soil, hungry power bills, and fragile machines. But the hardest part of living on the moon may be one that dust, cold, and radiation never touch. It works on the mind. Because the moon does something to a human being that no amount of engineering can fully fix. It leaves you utterly, terribly alone. Every danger so far has attacked the body or the machines. This one attacks the mind, and it may be the quietest killer of them all. Humans are social creatures, wired over millions of years for company, for open skies, for a living world all around us. A moon base offers none of that. It is a small sealed box buried in rock, holding a handful of people in the most lonely place any human has ever tried to live. Start with the smallness. A base is cramped by necessity. Every extra inch of space costs a fortune to build and shield. So the crew lives packed together in tight quarters, the same few faces, the same few rooms, the same low hum of machines, for months on end. There is no going outside for a walk in the fresh air, because outside is a vacuum that would kill you in seconds. The walls close in, and there is nowhere else to go. Then there is the sky, On the space station, astronauts orbit close to Earth. They look out the window and see home right there below them, huge and blue and alive, the continents rolling past. It comforts them. On the Moon, Earth is far away, a small blue marble hanging in the black, no bigger than a coin held at arm's length. You could cover your whole home planet with your thumb. Everyone you have ever known, every place you have ever been, shrunk to a dot you can hide behind your hand. Psychologists have a name for the strange, heavy feeling this can bring. Some astronauts describe a deep unease at seeing Earth so tiny and so distant, a loneliness unlike anything on the ground. On the Moon, that feeling could settle in and stay for the entire mission, and help is impossibly far. If something goes wrong on the space station, a rescue ship can reach it fairly quickly, and it can drop back to Earth in hours. The Moon is days away at best. If a crew member breaks down, or the group falls into conflict, or someone simply cannot take the isolation anymore, there is no quick way home. They are stuck together in the box until the mission ends. Even talking to Earth is strained. The Moon is far enough that radio signals take a couple of seconds to travel each way. A conversation with home carries an awkward delay, a small gap after every sentence, a constant reminder of the vast distance between you and everyone you love. It is a little thing, and over months it wears on people. Picture living in a small windowless basement with the same few people, unable ever to step outside, while your entire world hangs in the darkness as a dot you can blot out with a fingertip, and the nearest exit is days away. Now stay there for a year. That is the psychological weight of the Moon. History shows this matters. Crews on long, isolated missions on Earth, in submarines, in polar stations, sometimes crack under the strain. Tempers flare. Small problems grow huge, and those are places you can eventually walk out of. The Moon offers no such door. A base can be engineered against dust and cold and radiation. The human heart is harder to armor, and a crew that falls apart inside is just as doomed as one whose walls fail. So far we have counted the Moon's own weapons, but the deadliest obstacle of all waits down here on Earth, and it comes down to a single staggering number. For 28 chapters, we have faced the Moon's dangers: dust and cold, radiation and quakes, loneliness and toxic soil. Any one of them is a fearsome problem. Yet the real reason a permanent base keeps slipping out of reach is none of these. The real reason is money. Space is astonishingly expensive in a way that is hard to picture. Every single pound of anything you send to the Moon, every bolt, every sandwich, every drop of water, costs a small fortune to launch, and a base needs to send an unthinkable amount of stuff. Habitats, reactors, diggers, rovers, shielding, supplies, and the ships to carry it all. The bills pile up into numbers that stagger even wealthy nations. Look at what America's return to the Moon effort has already cost. The program built to carry astronauts back has swallowed roughly $100 billion so far. And what has that bought? A couple of test flights. A trip around the Moon. Astronauts have yet to set a single boot back on the surface. $100 billion, and the base itself has barely begun. The base alone is expected to cost tens of billions more spread over many years, and space projects almost always end up costing far more than promised. Studies of these programs have found billions of dollars in overruns, costs ballooning past every early estimate, deadlines sliding again and again. Here is the problem with numbers that big. Governments have to choose. That same money could build hospitals, schools, roads, or fund 100 other things people want right now. Every year, leaders have to decide whether the dream of a moon base is worth billions that could go somewhere else. And a moon base is a slow dream, one that may take decades to pay off, if it ever does. That makes it an easy target whenever budgets get tight. Picture trying to build the most expensive structure in human history, in the most dangerous place humans have ever worked, where every screw has to be flown up on a rocket, and knowing it may take 20 years to finish if the money holds. Now imagine having to convince a new set of politicians to keep paying for it, year after year, decade after decade, without fail. That is the true wall. The moon's dangers can be engineered against, given enough money and time, but the money is never guaranteed, and the time is measured in decades. A base is a marathon of spending that has to continue steadily, through changing leaders and shifting priorities, far longer than most big projects ever survive. And history is littered with grand moon plans that died exactly this way. The science was possible, The checks simply stopped coming. Plan after plan has been announced with fanfare, funded for a few years, then quietly cancelled when the budget got tight or the leadership changed. The moon does not have to defeat our rockets or our engineers. It only has to outlast our patience and our wallets. And a base that needs decades of steady billions is terribly easy to starve. This is why the deadline always slips. The dream is real, the plans are drawn, and the money arrives in fits and starts. Never quite enough, never quite steady. And there is one more force that makes the money even shakier, a force that resets the whole effort every few years, right when progress starts to build. It is politics. A moon base takes decades to build, and there lies a deadly mismatch, because the people who pay for it change every few years. This clash between long dreams and short terms may be what dooms the whole effort. In the United States, a new president can take office every 4 years. Each one gets to reshape the space program, and moon plans are big, expensive, and easy to change, so they get changed again and again with each new administration. The pattern is almost tragic when you lay it out. Decades ago, one president told the space agency to build rockets and aim for the moon. The next president cancelled that plan and pointed the agency somewhere else instead. The one after that swung it back toward the moon again. Each change threw away years of work and billions of dollars and started the clock over from the beginning. Imagine building a house where every 4 years a new owner shows up, tears up the blueprints, and demands you start again with a different design. You would never finish. You would spend all your time redoing work and the house would never get built. That is what has happened to the dream of returning to the moon, over and over for 50 years. Even now, the current effort has been reshuffled and rethought more than once. New leaders have arrived, changed the plan, delayed the missions, and rearranged the goals. The date for landing keeps moving. The shape of the base keeps shifting. Every reset costs time the effort cannot spare and money that is already stretched thin. Here is why this is so damaging. A moon base is a slow, distant reward. No leader who starts it will still be in office when it's finished. So a president who spends billions on it may never get to stand on a stage and claim the glory. The reward goes to someone years down the road. That makes it tempting for each new leader to trim the slow, expensive project they inherited and spend on something that pays off during their own time in power. So the great enemy of the moon base may be the calendar itself. The base needs steady, patient support for 20 or 30 years. The political world runs in cycles of 4. The dream is a marathon, and it is being run by sprinters who each hand off the baton to someone eager to run in a different direction. There have been efforts to protect the plan from this. Leaders have spread the work across many companies and many places and joined with other countries, hoping that so many people depending on it would make it too costly to cancel. Sometimes that helps, but every budget fight is still a fresh chance for the whole thing to be delayed, trimmed, or scrapped. And this is why, after 50 years and $100 billion, the bleached flags are still the only mark we have left up there. The science kept advancing, the engineers kept solving problems, but the plan kept changing owners, and a plan that starts over every few years struggles ever to reach the finish line. Yet something new has entered the picture, something that might finally break the cycle, or might make everyone dangerously reckless. Another giant has joined the race for the moon, and this rival does not run on 4-year cycles. For decades, America returned to the moon mostly alone in its ambitions, and mostly at its own slow pace. That has changed. A powerful new rival has set its sights on the moon, and its arrival is scrambling everything. China has built a bold, fast-moving space program, and it has announced clear plans to land its own astronauts on the moon and build its own base, aiming for the South Pole, the same region full of water and sunlight that everyone else wants. China is not asking permission, it is simply going. And China has an advantage that worries American planners. Its leadership stays in place far longer than 4 years. It can set a goal and pursue it steadily for a long time, free of the constant resets that have plagued the American effort. Where one nation keeps tearing up its blueprints, the other can keep building from the same plan year after year. In a race that rewards patience, that steadiness is a serious edge. This has lit a fire under everyone. Suddenly the moon is a contest again, and national pride is on the line. Leaders who might have let a slow, costly moon base drift now push to fund it, warning that the rival must get there second, not first. Competition, it turns out, loosens wallets in a way that pure science never could. The race is now one of the strongest reasons the money keeps flowing at all. But a race has a dark side. When you're rushing to beat a rival, you're tempted to cut corners, to skip careful testing, to launch before you are truly ready. Space is brutally unforgiving, and haste in space kills. The pressure to plant a flag first could push a program to take risks it should avoid. In a place where a single mistake can cost lives, there is a grim history here. The first space race decades ago drove astonishing achievements at breathtaking speed. It also came with disasters and deaths, as both sides pushed hard and fast. A new race carries the same danger. The urge to win could override the caution that keeps crews alive. Picture two teams racing to build a cabin on the peak of the deadliest mountain on Earth, each desperate to finish first, each tempted to skip a safety check to save a week. On that mountain, a skipped check can bury a team. The moon is far less forgiving than any mountain. There is also the question of what happens when both arrive. If two rival nations build bases near the same small pocket of the moon, both chasing the same craters full of ice, the stage is set for tension. Who gets the best spots? Who controls the water? What happens when their machines and their crews end up neighbours on a lifeless world, far from any referee? That question leads somewhere the law has never truly settled. Because for all the flags and all the plans, there is a strange and unanswered problem hanging over the entire moon. Nobody actually knows who is allowed to own it. Here is a question that sounds simple, and turns out to be a legal swamp. If you build a base on the moon and start mining its ice, is that ice yours? Who owns the moon, or any piece of it? The honest answer is that nobody really knows. The main rulebook for space was written long ago, back in the first space race. It was signed by many countries, and it says something clear and grand. No nation can claim the moon as its own territory. The moon belongs to everyone. No planting a flag and declaring it your land, the way explorers once claimed islands and continents on Earth. That sounded wise at the time, but it left a giant gap, and that gap is now a problem. The old rules say no country can own the moon. They say almost nothing about whether you can own the stuff you dig up from it. This is where it gets tangled. Suppose a company or a country lands at the South Pole and starts mining water ice, turning it into fuel and selling it. They would say they own only what they scoop up, while the ground itself stays free for all. Is that allowed? Different nations read the old rules in different ways. Some argue that whatever you extract is yours to keep and sell. Others argue that the moon's resources belong to all of humanity and cannot simply be scooped up by whoever gets there first. There is no court in space to settle the argument. There is no police force on the moon. The rules were written for a time when reaching the moon at all was the whole challenge, long before anyone had to worry about competing bases fighting over the same frozen crater. Now, imagine the collision coming. Two rival powers land near the same tiny region, the only region with easy water, each building a base, each needing that ice to survive. One starts mining a crater, the other also wanted. There are no clear rules to decide who is right, and no referee to enforce them anyway. That is a recipe for conflict, on a world where conflict could be deadly for everyone on it. Picture a gold rush where the map has no borders, no sheriff, and no agreed law about who can dig where. Except this gold rush is happening on an airless world where a single act of sabotage or a single accident could kill everyone nearby. The stakes could hardly be higher, and the rules could hardly be blurrier. This legal fog is a real barrier to a permanent base, quieter than dust or cold, and just as stubborn. Companies are wary of pouring billions into mining the moon when they cannot be sure their claim will be respected. Nations eye each other with suspicion. Without clear, agreed rules, every side moves carefully, slowly, watching the others, afraid of both losing the prize and starting a fight over it. Sorting this out means getting the world's powers to agree on new laws for a place none of them can fully reach yet. That is slow, delicate work, and it is barely begun. Until it is settled, the ownership of the moon hangs in the air unanswered, a storm cloud over every base plan ever drawn. So we have crossed the whole broken landscape now, from the glass dust under our boots to the legal fog over our heads. It is time to stand back and face the hardest question of all. After everything, will we ever truly call the moon home? We have crossed a broken, brutal world together. Now comes the question that has waited behind every chapter. Will humans ever truly live on the moon, permanently, for good? Let us gather what we have learned. The moon attacks with glass dust that ruins machines and scars lungs. It freezes for 2 weeks in a night colder than Pluto. It bakes for 2 weeks more. It pours radiation from an unshielded sky and hurls solar storms with little warning. Its weak gravity wastes the body away. Its ground shakes and its slopes slide. Its landing blasts sandblast everything nearby. Its soil poisons crops. Its isolation crushes the mind. And its price tag staggers the richest nations, while politics resets the whole effort every few years, and the law cannot even say who owns the place. Any one of these is a hard problem. Together they form a wall. Here is the honest truth, stripped of the glowing pictures. Each single danger can probably be beaten. We can build dust shields and nuclear reactors. We can bury bases in rock or hide them in caves. We can grow food without soil and pile up shielding against the rays. Give engineers enough money and enough time and most of these problems have an answer. The trouble is the word enough. Enough money means many tens of billions of dollars, flowing steadily for decades. Enough time means a patience that outlasts many changes of leadership. And that combination, huge steady money over many patient decades, is the rarest thing of all. It is the one resource we have never managed to keep pointed at the moon for long. That is the real reason a permanent base may never come. The moon does not have to win every battle. It only has to make the whole project so slow, so costly, and so dangerous that our patience runs out before the base is done. And history says our patience runs out fast, so picture 2 different futures. In one, humans finally muster the will, keep the money flowing, solve the problems one by one, and build a lasting home on the moon, the first permanent foothold of our species on another world. It is possible. The science allows it. In the other future, the more likely one, we keep visiting. We land now and then, plant more flags, run experiments, stay a while, and come home. The moon becomes a place we go, again and again, without ever truly settling. A campsite instead of a city. A place we reach, then leave. There is something humbling in that. We stood on the moon more than 50 years ago and dreamed that cities would follow within our lifetimes. Instead, the moon quietly showed us how hard it truly is to stay. It taught us that visiting a world and living on it are separated by a gulf far wider than the distance between here and there. Maybe that changes. Maybe a new generation, driven by the race and armed with new machines, finally plants a home that lasts. Or maybe the moon remains what it has always been to us. A bright and beautiful neighbour we can reach, walk upon and marvel at, yet never quite hold. The flags are still standing up there, bleached white by the sun, waiting. Whether they ever gain permanent company is a question the moon, in all its cold and silent difficulty, has left for us to answer. And the answer, it turns out, may say less about the moon than about ourselves.